Welcome to our lecture today on how to analyze a structure. This is going to be going through an introduction to structural engineering design. How do you actually take a building and convert it from a bunch of lines on a drawing to an analyzed model into a completed structure? What we're going to be looking at is various three-dimensional models and even some pictures of completed structures, but also some analysis models. We're going to look at various things: load path, analysis models, structural considerations, some preliminary designs you can check, calculations, creating an analysis model in Procon. We're going to consider various structures. We're going to have a look at a new warehouse, a double-story factory, and also an extension to an existing warehouse. I'm just going to pull up my first model now. This is a warehouse built in Johannesburg. It's actually part of a whole complex of warehouses. You can see here they're all very similar to each other. But we're just going to have a look at the one in the corner there. If you've got this warehouse, first let's go through all the terms. Let's see what makes this up. What are the names of the various components that characterize it? Well, first you've got our girts and purlins. Those are the things that carry the sheeting. So these are the purlins on top, our girts on the side. The sag angles, those are the sag angles in the other there. They support the girts and purlins. They prevent them from twisting and warping, and also prevent them from sagging while they're installing them. If you don't have the sheeting on it, these sag a lot downwards, so they prevent all that sagging. Then we've got our columns here, columns all the way around. This is the gable face, so these are gable columns. Got some internal columns there. We've got trusses. These trusses here. Come this side and cut a section through. And come this other side and cut a section through. The software we're using at the moment is called BIMSIGHT. TIKLA BIMSIGHT. It's provided free of charge. So if you can get hold of any models, you can actually view them in BIMSIGHT. There we go. This is a truss. And the models are kindly provided by Alan Petson from BS & Baker. So thanks, Alan. They're looking good. There we go. So this is a truss now. A truss sits on a column, and the trusses are supported by girders. So we now come across. And I'll show you the girder. So the girder is this structure in the middle. This part of the overall structure. That's another section. Have a look at it. Some of our neighbours' buildings for shame, so let's get rid of that. There we go. That's the girder in the middle. So the girder carries the trusses. And it carries the trusses then from column to column. And this way you don't need columns everywhere. Otherwise you'd have to have a column on every truss line, so you'd end up with hundreds of columns rather than just a couple here and there. So girders are very useful for that. And on the outside of the building, let's take the sections back. We've got bracing down the side. This is vertical bracing. This is horizontal roof bracing. Same this side. That's actually there we go. And vertical roof bracing there. And we've got some more bracing in this outer bay. There we go. Roof bracing, vertical bracing. And as you see, the gable columns. Then we've got our walls all the way around outside. We've got our foundations, our bases, and our columns. Our columns are plinths. And they're made of concrete that support our columns. Our base plates that link the concrete to the steelwork. These are knee braces. These are knee braces that prevent the warping of the columns. And those are the main items of the structure. There are other items such as door frames, roller shutter doors, the canopies on the front. But at least that for now is the main issues. Now, when we look at this, first you have to get your geometry right. The geometry is governed by various things. Obviously you've got certain clearances that need. Let's just go back to our section and have a look at it, so you can see what might be a consideration for creating this. Now, one thing I didn't mention, this on top is what you call a monitor. This is for allowing light. It's this little light steel thing on top. You put translucent sheeting on it, it lets light in first. So when you look at this building, there's obviously height requirements that they need to put various things in here. Height requirements. This warehouse was actually just rented out as a general warehouse, so it could have been for storage or factory or various things. So it's a general purpose warehouse we've got here. Then the slope of the roof might be aesthetic, might be architectural, the various things. I think this was a 3-degree slope. Normally 5-degree leaks less, but the architects quite like 3 degrees because it gives you a much flatter roof. Alright, so that would govern then the spans, obviously how much area you need, so that would influence what system you use. If you can have more columns, you obviously have shallower trusses. And let's go back. And the number of bays, if I come through here and pull this building out, the number of bays is governed a bit by selection. First, and by bay I mean the distance from column to column. Normally this is between sort of 5 and 7.5 meters. On bigger buildings it might go to 9, even 12 meters, but it just means you have very, very, very big purlins and girths. So there's a balance. Normally the bigger the building, the bigger the bay, etc. But there's a balance between making your girths heavier and having less trusses, but then your trusses get heavier as well. So there's an economics in this. Alright, but let's start having a look. How might we analyze this? How might we actually carry loads from whatever load is applied all the way to the ground? And obviously we have our dead load or our permanent load, which is the structure, our live load, which is a variable load, which could be people walking around on top, services, fire extinguishers, pipes in the roof, ducting, all those sorts of things. And wind loads applied to this, and there might be various others that you need to consider, snow loads or earthquake loads, etc. For South Africa, we're not really looking at snow loads or earthquake loads. But this is quite a complex structure you're looking at. If you wanted to put that in a 3D model, you can just imagine modeling all of this. It would take a lot of time, a lot of effort, and also you add in things that might not be 100% modeled, and it will add stiffness where on site there may not necessarily be that same stiffness. So you've got to be very careful in producing a 3D model. It's not out the question, but just be careful, be warned. So what we normally do is carry 2D models and break this entire big structure, this entire big warehouse, into a section of manageable and section that you can actually analyze. And you want it to be in such a way that you understand the structure and you know where all the loads go. So you can imagine, let's say someone walks across this roof. You need to think to yourself, where do those loads go? Or if there's lots of ducting hanging these wheels, how do those loads get to the foundation? When the wind blows on this side of the building, how do those loads get supported? If you don't know where the loads are going, you have a very big problem. That may mean your structure is not stable. You need to be able to say, if any load is applied anywhere to the structure, you know how it gets into the floor. And also when load is applied to huge areas, you've got a wind load applied to this entire roof and all these sites. How does that get into the ground? And how do those loads come together to produce a structure? Normally what you might have learned in structural design is how to analyze simplified model. A UDL on a beam, or a couple of point loads on a beam or column or something. Hopefully you've been exposed to fixities. This is a fixed connection which takes both prevents translation X and Y and moment Z, so it provides a reaction, a sort of shear reaction, axial reaction, a moment, a pin which prevents translation, a roller which can move sideways but not up or down, and a slider which prevents rotation, so it provides a moment support, but it can move sideways but not up or down. But these we've hopefully have been exposed to. These we've been exposed to, and maybe even trusses. But how do you make a structure look like those things so that you can model it? And how do you get loads from one part of the structure to another? And that's now what we're about to look at. Let's first take one of the simplest elements on the structure. Let's take a purlin here. Here we go. Here we've got a little purlin. How would you analyze that? Well, quite simply. It's a UDL. So simply supported beam with a UDL. If it was a continuous purlin, so go back there, maybe it's this one. If it continues across 2 bays, maybe it's supported at mid-span then, so you'd have to go back and add in another support. I'm just going to copy this across. We're working in AutoCAD Lite right now just to do some of the sketches. There we go, so that might be your purlin. Normally, you can often just design them as simply supported, but you may need to check for multiple spans depending on what's stipulated, or you can just state that purlins come in single pieces, but often the contractors like to erect these covering multiple bays. It really depends on how they're erecting it, especially the girts. You can put one girt covering 2 bays. It just makes the work quicker. Right, so we can analyze this though as a simply supported beam spanning from truss to truss. These can be designed to support these are the knee braces. The knee braces stabilize the truss, but we'll look at those later. But sometimes you can ignore these depending on how it's designed. You can see these are very slender, so if load gets put into them, they'll just buckle out the way. So we're not going to worry about them for now. We're going to look at something like that, which is spanning from there to there. Once you've analyzed it, then you can size it. You can size it for deflection. You can very quickly get the I required, the second moment of area required to give you a specific deflection limit, whether it's length over 180 or 250 or whatever deflection requirement that you require in your code. You can size it and then check for strength. In steel, it's often that's deflection governed, and then you check for strength. But now we design it and it gets reaction. What provides this reaction? Where does this force come from? Because obviously we can push on that purlin, push down on it, but where does this upward reaction come from on the structure? So let's go look back at it. Obviously from the truss. If you're looking at this, you can see that the truss supports the purlin. So I'm just going to go back to our little truss there. Okay. So all these trusses that sit all these purlins that sit on top of the truss. Purlin, 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 and all down. And here you've got the girts. And those are supported by this truss. So if you have a look at this truss, let's go back here. If you get this reaction now could actually be applied to this truss. So let's go put that on here. And this now comes down in all these different loads. And that is the way you can start sizing it, because what you do here, you size this for your live load, or you analyze it with a live load, and you get a reaction and a dead load, etc., etc. And suddenly you have a load that you can apply there. You can apply those all the way along. With this many point loads, though, what you'll find is it almost approximates out to a uniformly distributed load. So, depending, you have to be careful doing it, because it's an approximation of all these point loads, but you could otherwise provide a UDL all the way along. This would be upward for wind load, or you could provide one down for live load. Just leave it on the top. You'd have to rotate this around. Then you'd have a load coming straight down for your live load, or your dead load, or whatever it is. There you go. Coming straight down. So you can analyze this, get your reaction, and put it there as a UDL all the way from one side to another. So you can set up this truss model and start analyzing it. But if you look at this truss model, how is it supported? It's very clear to see now. We've got a pin there and a pin there. But where there are loads going, now what sort of fixities do we need to add to this model, this truss model? There we go. I'm looking at it now in Procon. Let's go back to our. What fixities do we need to add to this to support it? So you can imagine, let's say the wind comes across, and while the wind is blowing there's dead and live load pushing down there. Where do those loads go? If you look at this end, it's very obvious. Oh, of course they go to the support column there, and they go to the support column there, but they also go to the girder here. So, if you're going to add a support, you can add various things. First, we're going to have to add some fixities. At the bottom of our concrete columns, we've got a fixity, so we've got a fixed connection there. But how do we model that? If there's load coming down there and it sits on the girder, remember we looked at the girder just now, this can't deflect. The girder is normally very much stiffer, so we can approximate that girder putting in a support. So what we want to do is add something like this, a roller support. Copy and put it on. This allows movement in the horizontal deflection direction, but not in the vertical, so it can't go downwards. And when we analyze it like this, now we're going to get a reaction here. Take that out of the way. And we're going to get a reaction on our girder. Let's call that P2, let's say. And once again, we must ask the question, where does that load go? It's due to the girder, but let's first have a look at this whole frame. There's something else that might be an issue. If you look at this frame, it's not that stable. How are we supporting it horizontally if you've got a big load? Take a load here. And you push it across. You push this structure across because there'll be wind load here. There'll also be suction load on this side, so you'll be pushing across, pushing across. At the same time, you'll have uplift wind pressures or possibly downward wind pressures on the roof. So this is all pushing across. You need to stabilize it. You could design these columns and these concrete columns shown in green to carry the load. Or what you do is you stabilize it using roof bracing. Let's go to our model. How does this load get horizontally? So let's just take our section here. Let's take up the whole building. There we go. Load is applied horizontally. It comes across, it hits here. And this truss now tries to push across. So what we do, we provide roof bracing. It's basically like a giant truss all the way along the edge. So if the wind comes from the top, pushes down on this truss along grid line AD, pushes, 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 it comes all the way down the truss to here, and at the same time with the suction pressure you're pulling this down, it will come. But this very stiff truss, this very deep truss almost, prevents it from moving. And that provides the lateral stability. So the load comes down and then puts these members into tension. Now if you look at those, these are very long, thin members. So obviously they can't take compression. You can just imagine on the side. If you pushed on these things, they just sag out the way. But being steel, they don't have to be very thick to provide immense tensile stiffness. So these are tension-only members. However, to make sure this works, you've got to have something at the top, which is that blue. It's a blue pipe. There, and there's a pipe here somewhere. It should be, I think. And there's one there. And that carries then the horizontal loads, or the top and bottom. So I'm going to go back to our model. You can create a model that looks something like this. With this is the roof bracing that we were looking at a few moments ago. Plan. There we go. There's our roof bracing. And once again, where do these loads go? So now I can analyze my truss. I get a reaction. Let's call that P3 now. Maybe it's called. We'll call it horizontal load, just so you don't get confused. There we go. Horizontal 3. There's a horizontal prop. There we go. It is carried by this. This now is carried by this truss. Or we can draw it around either way. Let's have a look at it this way. So let's say this now truss supports that. So we're going to orientate it like this. I'm just going to try to get everything in the same direction, just to not confuse you, hopefully. Yeah, so there's my the roof bracing coming along. So I get my horizontal load here, and now I can apply this to here. And that is how you take load from one part of the structure to another, all the way along. Once again, how is this supported? But before we get that, think about that question when we come back and finish off this model. Right, we've got this, but there's also a couple of other things missing. There's one missing. How are we considering this connection from the steel in white to the concrete in green? If it's a fixed connection, what's shown here is fine. If it's a pin connection, however, you have to be careful. What you'll need to do in your analysis model is actually add in a pin. There. And there. There we go. So you add in a pin so that no moment is transferred. That's quite commonly done, so you only put horizontal forces into your columns and your foundations. If that is too not stiff enough, though, you can make that a fixed connection. Alright, so let's have a look now at our analysis model. Here we go. Truss. There's our girder support. There's our lateral support for vertical bracing. There's our pin. So if we analyze this, wait, before we analyze, I need to show you my loads. I've got various loads that we'll put on the structure. There loads. There's dead loads coming down. Live loads coming down as well. Wind loads. Wind load launch, as in from 0 degrees, so across the building. I've got wind load on this side, upward pressures, wind load on this side. Also got a wind load 90 case. That's if the wind is blowing onto the gable face and then causes suction. So it causes suction out on that side, suction out that side, up and up. And there's also other wind load cases that you can take with the new South African loading code, which is very similar to the European loading code, where it's up, down, up. You have various load conditions. Sometimes it gets a bit much, all the load conditions. So often the older engineers especially, they just do one or two load combinations, but the new load, the loading code does provide for a variety of loading conditions. But let's have a look at this wind loading case. If we've got horizontal, up, but let's combine it now into various things. We have our load cases here with dead load, live load, etc. And this will also consider some notional horizontal forces if required, or second order analyses. But here we go. Got dead load and wind load, dead load, wind load, etc. So you've got various wind load combinations we consider here. These serviceability ones I just put in there to assist design, so you output serviceability forces and reactions, but you don't need to worry about that. Alright, but here we go. We've got dead load, wind load, 0 to 90, 1.2 dead, 1.3 wind, and live load's been reduced. It's factored down since it's unlikely that the maximum live load will occur at the same time as the maximum wind load. But you can play with those wind load combinations depending on the structure. And then we analyze this. Make sure it's a second order analysis, or you need to add in notional forces. Here we go. Let's analyze this. Do you want to continue? I think I played with something in the model there. That's not serious. The output. Here we go. We've got the forces. And here are reactions now. I've got my dead load reaction, my live load reaction, my wind load 0, wind load 90, and you can see the horizontal and the vertical reaction. So now I can take these and just put them on the next model, or I can just take the entire reaction, load case 1. 118.53 kilonewtons, put that. I normally personally prefer putting the different combinations, so I take the dead load, live load separately, and then put these on the next piece of the structure, and then combine them once again. It makes it easier, especially when it comes down to foundations where you've got serviceability, design, and the likes. Alright, so that takes us through our truss. But you can see now there's no column here, but there's a different type of truss that we might need to consider, which looks more like that. So there's actually another truss that we'd have to get to later in the structure. So let's zoom out. And that would be one of these trusses on a column line. But before we get there, we need some other loads. Because what we've been trying to do now is track the load. How does it go from one section to another? So we started at the outer members, so we're taking it from sort of primary to secondary to tertiary parts of the structure. So as the load follows it, as it gets closer and closer to the support. So what we've done so far, we took load from girt to truss, from truss to column or to girder. And this truss now this column we could fully design from our model. We've got enough forces and moments. If we go to our forces, we've got axial forces and moments, etc. So we could go and then design these columns and even the concrete columns below. Just as a note, so you can see this base level here, that's not necessarily your floor level. Your foundations might be low. I'm going to go to a drawing of this. If you look at this, you can see your floor level, I think, was about there, and your foundation level was lower. Or if you've got a system, here we go. Sorry, this is where the steel stopped. This is our floor level, that red line. The base was below, so what you'd normally do is model all the way down to the base and then put your fixity there, so that would be fixed. Okay, now coming back, so now we've modeled our truss, our girts, our purlins. Now let's have a look at this girder. Here we go, this is girder, this is half of it. So if I wanted to set up an analysis model, it looks something like that. This is from one of the other structures in the complex. So the one we're looking at now is its symmetrically spaced columns, but it's the same principle. So here we go, so we've got this model. And once again, we can take our loads from this, from here, from up top, and we can put those now on our girder. Wherever the truss sits on the girder, we can now put our reactions wherever those points are. Let's say it's here, here, etc. And all the way through the structure we apply our loads. And this would obviously now be P2 and etc. So I'll go through just to show you how those apply. Well, the end one actually would often be P2 over 2 if you half, or if it's a rafter, it would be even less than that. But we'll come back and have a look at this force now. Calculate that, but all the rest of these will obviously be P2. The reactions though, now what horizontal forces would be applied to this? Because we've applied from wind load naught, our load combination when wind comes across the structure. So if we look at our model, wind load comes across the structure. But what happens if the wind blows from the other side? How are those loads taken? So you can imagine, I can apply a little load here to the sheeting. How are those loads carried? Same question. So obviously, this goes up the sheeting and down the sheeting to our girts, from the girts to the column. The column then, how do we design this column? This is very simple. This connection at the bottom could either be fixed or pinned. And the top, it's pretty much always pinned. So we carry our load now up or down. Once again, we get to a situation like this. We've got a simply supported column with loads. These could either be our girth loads, or we could define it as a UDL. If you want to do a quick design, this is more than sufficient, and even it's more than sufficient just to put a UDL most of the time. But how do you calculate the value of this UDL? Where would this come from? Well, obviously it's the pressure of the wind, but we're looking for value in kilonewton meters, kilonewtons per meter. It's a uniformly distributed load along this, or might be slightly non-uniform depending on the shape of the structure. But okay, we've got our UDL there. We've got our pressure from the wind, which you need to calculate before starting. Then what area would be carried to this column? Well, this is halfway between each column. So if I mark it up, hopefully I can draw here. There you go. So it's an area like that goes to this column in the middle. So all this would sit on that column. And that way you can very quickly get a load and design this column. You don't have to get lots of little point loads and have a very complicated analysis model. You can very quickly get an almost correct model. There you go. And you can design it. When you're designing it, you use these knee braces to stabilize it, so that shortens the effective length of the back column. From there, from the knee brace to the bottom, or from the knee brace to the top, or from, if there are multiple knee braces, from knee brace to knee brace. If the front flange is going into compression and it wants to buckle, it's supported from girth to girth, because these girths support it, but the back flange is unsupported. Alright, we've analyzed our column now, and one thing though, with these sorts of steel members, they're normally governed by deflection. So you check your deflection, get your deflection right, whether it's L over 180 or span over 180 or 240 or whatever it is. You can size your member very quickly with a straightforward calc. You can get what your I needs to be, and then your second moment of area needs to be, and then based on that, you can just look in the book and get a member size that's close enough or just above that second moment of area required. Let's go back to our model. Alright, we've analyzed our column. Once again, we've got reactions. How do we support these reactions? Well, the bottom one's quite easy. It sits that the model we've just looked at, the simply supported beam, is this section here. Well, sorry, it's actually not on this face, but it's on the other face. It's on this face along the gable edge. This column here, going up, going down. So here, the load will then carried by a cantilever. This column, this concrete column, you can model as a cantilever. It's fixed at the bottom, pinned at the top, or free at the top, with a horizontal load, which is the reaction from that. And that way you can size the column and size the base without too much difficulty. Now, let's have a look at the top. Where does this top load go? So the wind comes along horizontally. We need to get this load now into these foundations. And the way we do that is with roof bracing. We can provide a lot of stiffness to this entire gable face with roof bracing, whereby a load coming along hits it, and this is a giant truss all the way along the top. So if we go back to our model, there we go, giant brace all the way along the top. In the same way that we brace the trusses, we're bracing our gable face. So here we go. What are the fixity conditions? Where are we supporting this giant truss through our roof? Well, obviously it's at the side, so we get our pin support. Put it into where we need it to be. So we can pin it, support it, support it. Now, what happens in the middle? I'm going to put a support there, but why? But that load is carried by the girder. If you come back to this model, cut my section through here, you can imagine this bracing. The load comes along here, it goes all the way down the bracing to this girder. And this girder is actually very stiff, so it will provide an effective support because the girder works with all the columns. So it's girder plus column, 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 all the way along. So you end up with a very sort of stiff rhombial type action, and that provides the support to this roof. And at the side, you need to add vertical bracing to carry then the load which reaches the side all the way down to the ground. So let's go back to our analysis model. Here we go. We apply our reactions from our columns, or whatever load this is. We could apply here. Or once again, we can do a quick calc. What load you apply to this node? Well, same story. It's half the load will go up the column, half the load will come down the column. So it's an area like that, and like that will go into this node. So that way you can very quickly get what this load should be. It's just pressure of the wind times area. But remember, this is for pressure only on this face. If this brace bay is carrying the other face as well, you need to add in that face to this load. But you'll see why just now we actually have two braced bays for the gable, but only one for the trusses, right? So this load now will come into this brace, vertical, this horizontal brace all the way along the top. And there we are. We can quickly calculate our loads and then design for it. We can design this all the way along, and we'll get a reaction. From this, we get a reaction, which we then can apply to our girder. So there we go. Just going to put it which way should I put it? Okay. Let's call this D5 or something. Our reaction here, and this is our girder load. Now horizontal fire, so it's a horizontal load, and this we now add to our girder. There we go. So now you can see we're actually gradually tracking this load through the structure, and that's why I said earlier we need to come back and see what horizontal loads are applied. But when you do this, be very careful. If this horizontal load, H5, includes the whole gable face, you don't need to then go and apply another UDL on this. Or what you do is when you do the analysis model, you don't apply a load from this side. If you've got all your loads coming down from your gable columns on top of it, let me show you that. So you've got all your gable columns loading this structure, or you could possibly otherwise put a UDL. But these spans, it starts getting a little bit more difficult to do that with these long spans. You can analyze this one. Just be very careful if you add this one in. Don't double count it, so then you go and add it again when you analyze this model, or you leave it off the model and then you add it separately as a UDL on this column. When you analyze this model, be very careful once again. This is, the members are tension only members. So typically what would happen, is explode this so I can delete some members. If you're unfamiliar with using AutoCAD, feel free, there are a number of AutoCAD lectures that we've produced online that you can go refer to. These are tension members, so what happens is, let me actually show you why I'm doing it. When this goes into bending, obviously this bottom will go into tension and might go into compression over here. It's to make it so I'm just going to remove it. Yeah, I'll leave it for it actually. This will go into tension and then compression, tension, etc. and then compression, tension. These internals will go into a series of tension and compression. Let's say, simply speaking, I only leave the tension ones because the rest of them, if they go into compression, as we said earlier, they buckle out the way. So, let's explode those as well. Explode those as well. You need to make sure that you, when you design it, you don't necessarily have to delete them in the model. At the end of the day, you have something looking like that. You don't actually have all the roof members. And in your model, the way you simply do that is you make sure, as I said earlier, it's a tension-only member. I don't have one of those models open now, but if you go to these cables, sorry for the sections, make it tension-only, but then you have to have a second-order analysis. It won't work with the linear elastic, so we go and change it to second order. If it's on linear, you've got a problem. Alright, so that then covers it, so that makes sure it's tension only, so that these are allowed to buckle out the way. If you're having problems with convergence with the model, you can actually physically just delete all these members away and design it that way. Be careful when you're modeling it also. I don't add a node at the center. I just add a section from there to there and a section from there to there. Sometimes you get funny things happening when you add a node at the middle here with tension-only behavior. Because these members are so long and slender, you can sometimes have numerical issues in the models. Right, but that considers now our girder. Once again, question one more time is, how is the girder supported? I'm just going to move this out of the way so you can see it's a structure. The girder needs to be supported by something. The girder will obviously span that way and span that. Not the girder, the roof bracing. It needs to be supported side. And so that's why we have this vertical bracing. The vertical bracing goes up, and that supports your roof bracing. So let's say we've got another horizontal load. We have a reaction here, and a reaction here. We call it H6, which would be more or less H5 over 2. It's half the central load. H6. There we go. And that load will now apply here, where this is our model. Of this bracing. There we go, there's our bracing. Back to our analysis model. So we'd apply a horizontal force of H6. And here we go, here we've got the model. And we've almost got our force all the way to the ground. We'll take it. I've just modeled the steel part at top and made sure these are pins here, but you could add the stuff below, the columns below as well. Why we haven't modeled these ones, or why we support them here, is the brickwork is very stiff, and if you fix the brickwork to the concrete with hoop irons or whatever, this brickwork is very stiff, so it actually stabilizes your structure, so you don't necessarily need to brace below it unless you have very high loads. So I've modeled this top part, and that'll carry the loads all the way down. In this bracing, go back here, before I've said it's tension only, but just be careful, these diagonals of tension, these horizontal members need to be designed for compression. So what we normally do is make them circular circular hollow sections, which is a pipe basically. You have a pipe here, circular hollow section, and this thing can carry the load. So the load will come down in compression, tension, compression, tension. So at the end of the day, oops, deleted too much there. Explode this so I can show you what's been. So go compression, tension, compression, you'll buckle out the way, tension, and there you go. You can do this by hand very quickly. And if you really wanted to get a rough thing, that H6 can be determined quite easily. Because once again, what area acts on that? If you look at it, so obviously this load goes this way, this load goes this way, and some goes to the central column, some goes upwards, some goes downwards, so let's mark it up. So, some load goes upwards, some load goes downwards, some load goes that way, so we divide it in half. Right, so, there we go. That's the area here that gives you H6. So, when you do your model, it should be more or less that. If it's a statically indeterminate structure on top, you won't have it with fixities. Obviously, if this is, it might attract a bit more load to the center. But roughly, you can actually calculate that reaction simply by a quarter of this face or an eighth of this face. Apply it all at that point, and you can get that load straight away. But remember, once again, that's only for this face. Whereas if you have suction pressure acting at the same time on this face, that will pull this, and you'll have a load from that same area this side. If you only have one brace bay, let's say you only have this brace bay or this brace bay, You need to add pressures from both sides, as I keep emphasizing. But one thing you'll see is now, why do we have brace bay both sides? Why don't we just bring those loads all the way here? Well, it's possible. Just imagine now. How are you going to carry all these loads? This is what we've been discussing. I need to get my loads into the foundations. But let's say this pipe didn't exist. This horizontal member here that carries my load. I'm going to hide it here. If he's not there, then the bracing is not here. How do I get the load all the way from here to here? Because that's where my stiffness is, my stiff basal. And said I have to put those circular hollow sections of those pipes all the way along the building, all the way from one side to another, to get the load into that brace bay. That's why you need to have a brace bay to support your gable columns. And when you do your building setup, you need to make sure your bracing matches your gable columns. If you don't have that, you've got a very big problem. Because imagine now if this gable column is in the middle. If this load pushes horizontally, where does it go? It doesn't have anywhere to go. So just push and then put this beam into bending. So either you've got to design this beam for bending, or you've got to put something there and get the load across. In the middle, you'll see these ones carry almost no load. But even so, they fix the bottom of truss, and we'd have to make sure that those little knee braces may, if there is any load that's going to carry those could carry it. Those are just temporarily in there, basically to support brickwork. Alright, in the analysis model, I may have forgotten to mention this earlier, when we're looking at this roof bracing, it's the same story, supported there, but if we've got a nice stiff concrete wall, this is a brick wall here, if we can link this truss to here, you can add another support to it and it drastically reduces your spans. So in this model, that's that. Or sorry, that would be this support here. I'm going to add a couple of supports. So in our roof bracing for the trusses, we've got a support there, and support there. And with that one, it's actually from the concrete wall, or the brick wall in the middle. There we go. So that would carry the load. Alright, so very quickly now, we've actually gone through quite a lot. We've gone through this whole thing. But before I do that, before I switch away to the next structure, what I want to show you today is how you also check, or how you get preliminary calculations. Let me just redraw this. What happens if you have to do a quick size on these foundations, or this column, or these reactions, or something like that? How would you get this force? If you think you have to do this whole model, it would actually take you a very long time, but there's actually very easy. You can get a reaction here at this point from this entire face. Well, how do you do it? As we said, you apply over whatever area catches us. So let's say it's from here to here. To draw that out. There we go. Across that area is captured at that point. Then this acts as a rigid object, this whole top bit. So you just take moments about here. This force times this distance equals this reaction here times this distance. And in three or four lines, you can actually get the foundation reactions very quickly, very easily, without having to analyze trusses and bracing and everything else. You can really break it down into something that you can approximate the design for. The same thing with this girder. You can check if you get reactions from your vertical bracing, or roof bracing, I mean. Does this load match the areas it's carrying? Does these vertical loads, is this basically half the roof? Get out of drawing the pictures here. The loads on the girder, if it's a dead or live load, it should be roughly half the span from here to here acting on this. So if we wanted to work out what is the load from this truss, what is the reaction down on this girder, once again, sort of half, and all of that would be acting on that one truss and providing a reaction force there in the middle. That way you can check your reactions, you can check your calculations, make sure there's nothing funny going. Obviously, if this is more stiff in the middle, so this would actually probably attract between 55 and 60% of the load, 55 and 60% of the load. But it also depends on the stiffness of the outer columns and various other things. But so it's half, but obviously the stiffer areas do attract more, so we might add on a little bit there. Right, but now we've actually just gone through an entire warehouse from start to finish in terms of steelwork. You can then size your girder, size your columns. You can get your reactions from your steel columns and size your concrete columns. So you'd get a force here. I should actually draw these bottom ones in green to show that they're concrete. Let me just do that quickly. So you have your concrete columns at the bottom, where the bottom of this column is where your steel is. And there you go, and you can then get your forces from your girder to your column and then put those all the way down to the base. And then if we're analysing this, we're going to add some complexities to it. All the way along, and you can get your model done. But now, as you can see, we're sketching this all up, but you can imagine even with a simple model like this, it can be a real pain to model this in something like Procon or whatever software you're using. You don't want to have to go and input all these little values. So it's actually quite a simple way. If you have a drawing, let me go to my drawing here. This was produced. If you've got this, you can create a Procon model from this. What you do is you simply draw over this, or if you've got a line diagram, you just come up with this, you draw over it, you get something like this, and you can actually import this into Procon. So I'm going to copy this, and then you go into a new drawing. I think I've just got one open already. And you create a separate file, either as a DWG or a DXF, and you can save this. When you create this, one useful trick, just remember this, is before you import it, just purge it. P-U-R-G-E, enter, type purge in AutoCAD, press enter, and it'll ask you, do you want to purge? If you haven't purged already, you'll select purge all. If there's stuff that you might not be able to see, but it's hidden in the background, it'll still load that into Procon, and you might see a million nodes appear. So it's useful to purge your drawing. Also, make sure wherever you need a node, let's say we've got our concrete column there, you have different lines wherever you need a node. So we'll add sections like that. They don't necessarily have to be different colors. Add it all the way along, so at least then you have a line stopping there, so you know it will create a node when this is imported into Procon. So we can draw this out, save it, close it. When you import this to Procon, if you have File, Import DWG, Save Changes, okay. You can go find this wherever it is and create it. When you import it though, just be careful. Let me see if I can show this to you guys. I'm used to see it. Apologies. It's going to take a couple of seconds to go to that area. What we're going to do now is go find that there we go. Analysis. Here we've got our DXF file, Procon model block A girder or truss. Let's import the truss. So we're going to open. Interchange. No. We want all our values to be as Y values. No. Oops, I don't have the most recent version. My apologies. But you'd go through those steps and then it would import it. And then at the end of the day, you'd create a model, like I showed you just now. Like this. One thing though that's often a problem, when it imports it into Procon, it renumbers the node. And then you can get crazy numbering all over the show. So it wouldn't be reasonably nicely noded. It could be 4, 127, 2, 36. It becomes very much more difficult to apply UDLs or distribute loads to this. So what you do is you just copy and paste all these nodes into Excel, you renumber them, or you just arrange them first by X or by Y or by both. You rearrange them, renumber them, and then just copy and paste them back in here. You actually then end up with a nice numbering. It does mean you have to recreate all these beams and columns, and you can quickly go through. And at least you've got nice node numbers that also when you're analyzing it, you can create it. So that's a quick way of creating the model. And then you can go through and create your beams, adding your beam sections. Make sure you select tension only if you need it. Supports. Here we go, X, Y, Z. As I was showing you earlier, that's translation plus moment rotation. And then all of these are applying moment rotations. Now the model I've got open is the main truss line in front. where the girder sits. This one is a bit more complicated to analyze because it might, if it's acting as a support, if this bay is much stiffer, it might actually act as a support for your horizontal bracing. So then this load you'd have to apply to this model here. If it's quite slender, then you don't, then the roof bracing takes it all up. In structures especially, we've got big concrete columns that go all the way up, and you must design it. I'll try to show you an example just now of how you might do that. But then you'd have to apply all the reaction load here to this one and then design that for it. And also, you might have biaxial bending or on this column, because this column is both part of your truss and part of your girder. So that's, there it is there, and there it is there. So you may have to consider the combined action of the columns in both the girder and the trusses acting, depending on your load cases. And also, this load, you may have to add a vertical load here from your girder. So be careful of all those things, that you don't forget loads, but you also don't double count loads. So you add on a load twice to the structure, or as I said, if you forget a load, it's even more dangerous. Right, but now we've actually gone through an entire design, how you go from a simply supported beam all the way through to an entire structure which you can analyze and design. So now let's have a look at another structure. We've gone through one at the moment, which is it's a fairly straightforward warehouse, but let's have a look at a different structure. We're going to have a look at this one now. This has got a big composite deck. This is steel beams with concrete on top, and then a sort of a portal frame. This obviously is a fixed connection up here, or it's a fixity from one to another. With the bottom, I'll show you just now, these are actually pinned beams. Because if you don't connect your flanges, you can't transfer moment or negligible moment from the beam to the column. So these become pinned connections around. And this structure, though, once the deck is cast, if you look through here, here we go. There's some pictures of the beams. And here's the deck when it was cast. Here's a concrete deck. Here's some bracing. We use this bracing to stabilize it. And here we go, and that's the completed structure with bracing on the front to stabilize that tall open bay. See they're all the way through. So we needed something to stabilize this bay, so that's the roof bracing across. There's cranes in here. This is the floor on top. There's cranes, etc. Let's have a quick look at a 3D model of that. While that opens, it's going to give just taking a bit of time to open that. In the meantime, I'm going to look for the drawing of it to show you what it is. Right, here's a plan of the floor. We've got beams, etc. supporting the composite floor. For this example, we're going to assume that these beams are not composite. They're just standard beams supporting the floor. And we can now do a load rundown in a very similar way as we might do with a truss. These beams, as I said, are simply supported. You don't connect your flanges from one to another. You simply connect the webs together. You have a cleat or a thin plate or something, and you connect this beam to this beam. So you don't pass moment from this one here to this one here. You can actually isolate, so you know the force stays here and you know the force stays here. These are just core beams bolted to the underside of it, or bolted to the beams and fixed to the underside slab, so don't worry about those. There we go. There's core beams, etc. And those support the floor. So what you're looking at this drawing is these beams here. Now, how do we analyze these beams? Well, exactly the same way as we were doing just now. We start off with a simply supported beam. What is the UDL? Well, either, if this is a one-way spanning floor, if it's a bond deck, or you get various panels which have a shaped profile on the bottom, it almost forces the load to go in one direction. You should draw. So if you don't know what a bond deck is, it might look like that. The bottom profile, and then you fill up this trough. You fill up this trough with concrete. This structure was actually flat. It was flat on the bottom, so it would span two ways. So you get triangular loads. So if you're going to analyze this beam, you might say, well, the beam load acting on it looks something like that. And obviously you'd mirror this and you get the load on the other side, and then you can analyze it. Or if you analyze it with a UDL all the way through, it'll start being a bit maybe a little bit conservative, But as long as you then, if you analyze this beam, you don't double count it, you don't add on another triangle. But the theoretically correct way is to add that and then a triangle onto that load, etc., etc. The way I've drawn it is probably even correct in terms of that this more load will be attracted this side and that side because this is stiffer. So this is fixed pinned because this is continuous this way, this concrete slab we're looking at. So 55-60% of the load will go here, where 40-45% of the load will go there. Alright, and you can then do the same thing. So these, and this just highlights how much load goes on each of these. But now, once again, we analyze our beam, simply support it, and then we do the exact same thing. We get our reactions, and then we go to the next beam, and then we put this reaction on top, and we might have 2 or 3 beams, and do it that way. For instance, let's say this is a panel, that shows that it's a one-way spanning slab, not a two-way. Means all the load, if I was designing this beam, the load area would be that. I can get a UDL, design the beam, design this beam, etc. Will that all be the same? And then those will put reactions onto that. And if you want to size that one quickly, this is basically a UDL from here to here. So you can just take the width, which would be 3 meters, halfway between, or if this slab sticks over, it'd be a bit further than 3. You apply it. And that way you can very quickly size floors. And once again, steel work, you normally size for deflection and check strength. So you can very get an idea of what size you're doing. And also, if you want to size this column, it's just this area. Or if this is it's 2-panel, be this area. Or if it's continuous, be that area. So you can also then get very quickly the load that acts on each column just by simplifying it into area and seeing what load acts on what area. But now, once we've analyzed these beams, let's go back to our pictures. How are we going to analyze this frame? So you can see this is sort of a portal frame type idea, where you don't have roof bracing. So let's draw that model out. So do a second one here. Well, we've obviously got our floor, so there's one of our floor beams. Then we've got another floor beam this side. We've got our portal frame on top. And those the columns go all the way down, so we have that. And we've got our roof on top. And these are fully fixed connections. You'd obviously have to draw this accurately. I'm just doing it very roughly for now. And we've got our column in the middle. If you analyze this, what do the supports look like? Where do you find support from? Well, obviously, you've got some fixed connections or pin connections, depending what your fixity looks like here. So let's say we're fixed. Let's say we are able to carry the fixed load here. Moment here. So we've got fixed load, fixed support, fixed support. But one thing also, remember, this is a concrete deck once it's crossed, so this becomes very stiff. And if you add load somewhere in the structure, let's see, there we go, here's my open 3-dimensional structure. You can see this is a very complicated job. We have to build it between existing buildings. I'm just going to cut a section here. Yep. Cut that. Here we go. And we'll take away the existing buildings, which are caused headaches in terms of trying to prevent leaks. But we eventually got there. There we go. What's not shown here is the floor. So we've got all these beams, and we'll have concrete across these beams. Now, we can support this. Rather than designing each of these as a portal, why don't we just add in 1 or 2 braces and we can support this whole floor? Because this massive concrete slab that will cover all these beams is so stiff that it will act as almost like a floor brace, like the roof brace. So, if we now add a bit of bracing on this side, I'm going to add some here, and bracing there, K-brace, that will allow people to drive through, or we could add in a cross brace. And we add in a K-brace here. K-brace. There we go. You can actually then span the load from there to there, and then the lateral load can be taken by this floor, and then taken all the way down to the end bay, and you can just design that brace to carry the load. So let me go show you how you modify this model. So you've got that. What you simply do is you add hip hop to it. So put here. Let's just rotate it about the other direction. So I'm just going to rotate it just so you don't get confused. Rotate. We'd add a prop like that, and we'll just let me move it out the way. So it's there we go. You add a prop, and this is force that you then take all the way down to the bracing that is here, that I've just drawn in, and here. And in that way you can stabilize the structure. And you can use a diaphragm action, a diaphragm of the floor here, to stabilize this entire structure. And especially, I mean, if this was, let's say, a concrete structure here with a steel structure on top, it'd be the exact same story. What you might just add in then is a pin here, and a pin here. Once again, you prop it there and you can stabilize it. Or if you have to, you make it moment, and you can really carry the loads more efficiently if you know where it's going, if you know where floor bracing, roof bracing, etc. Let's say now there's no concrete slab on this thing. Let's say the floors look like that and there's just some grating on top. How do you do that? Well, you've got to carry the load sideways. So you could even brace this whole floor out. And you can make the floor brace the structure. Something like that. And this then becomes a kind of a truss. And you can use these if there's a horizontal load there. You could actually transfer it through the structure. So there are many ways to carry it. One thing you must remember is you have a look where all the load goes and where can you take it to where it can be efficiently handled. So you can add pieces to your structure, and you must add pieces to your structure that you can then transfer it. So especially in this, with this deck, you only need to add one brace each side, and you stabilize all these portals. So it's much more efficient to do it this way than to design each frame as full moment resisting. So there are various different ways you can consider that. And that's how I have a look at another model. I'm just going to go to the warehouse extension. This is another model I'm going to open in a minute. It might take 30 seconds to open up. And this was an extension to a warehouse. What we did, there was an existing warehouse with the exact same profile, and we just added on some bays on the end. I wasn't directly involved with this, but once again, thanks to the BS & Baker guys for the models. There we go, as it's busy loading up in Tekla. On BIMSIGHT, there we go. Here is our model. And what's quite nice is you can actually see there's our sheeting. So you can imagine wind coming on, hitting the sheeting from this side, or wind coming on, hitting the sheeting. And just be careful on these big warehouses. Have a look at the wind load code. You also have to consider friction forces on top. Friction forces come and they are generated as the wind travels across. You may need to add those as horizontal loads. So now let me just turn off my sheeting. There we go. Here's our structure. Now where are all the loads going? Wind load blows on the stable column here. Wind load goes up, wind load goes down. As you can see, this had to be stabilized this way, so it carries load to this point. And then it goes down the roof brace, all the way to end, all the way to the end. Uh-oh, no vertical bracing. Why is that? Why is there a problem? Well, not actually, because that load came along, and then we transferred it down these pipes, those horizontal circular sections, into the existing building. Because the existing building, which you can't see here, could support it. There was a stiff brace bay here. So you can also transfer load down things through pipes. For instance, let's say you couldn't put braces here for some reason. If there was penetrations to the roof or ducts or something weird, and you couldn't put a brace bay here, you put it in the next bay, then you just take your pipes all the way through. So you go through that bay. So there's your pipe in orange there, I've highlighted. You just put one there and one there. You can take your load down there and then take it out the door. So that's ways you can actually move forces through until you can get them to a place where you can handle it. So now I hope that has given you a very good introduction to structures, because you need to get an understanding. When you look at a structure, say, if wind is applied from there, if dead load comes there, if live load, if all these sorts of loads, how do I carry it through the structure? So now we're going to have a quick look at some other constructed buildings. This was one I walked past that's at the Cape Town waterfront. I wasn't involved with it, but quite a nice looking structure. Just a simple composite structure. These are probably fixed connections or haunched connections on top, steel sitting on concrete, etc. There's currently no bracing. I don't know whether they'll add bracing in the future or they did before it's finished. But let's say now wind blew there. As you can see, there's no bracing in any of these bays that you can see unless, as I said, it comes along later. So how would you get it to the rest of the structure? Well, diaphragms, you've got the floors, so you can use your concrete floors to take it to your lift shaft, or wherever it's, let's say a lift shaft, which is a nice stiff poly structure. To analyze every little bit and piece is going to be a nightmare to get the loads on your lift shaft, wherever it is. So, you just take your tributary area and pressure and suction. You can quickly then get a horizontal load which you apply to your lift shaft, and you can size your lift shaft or your brace floor or whatever it is that provides lateral stability. And same thing with columns. You can say the areas and get a load run down and get your foundation loads. And that's why you need, if you can look at a structure and see where the loads are going, you're in a much better place to first produce preliminary designs. You can have a quick calc to say, well, this area, blah, 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 here you go, rough estimation of foundation loads, piling loads, etc. And also then, where do you put bracing, where do you put all these things? We'll have a look at another side. It's the same picture. Here we go. Here's another structure. Multi-story. Here we've got concrete floors. A wind load comes along here, and here's your braces. This braces it out. And roof bracing, same story. Wind load goes up, wind load goes down, through the bracing down. Dead load, live load comes down your trusses, down your columns, down your trusses, down your columns. And this way you can really analyze an entire structure by breaking it up into simple components. Right, so let's go back. So we've discussed load paths, analysis models, structural considerations, all these other things that now you should hopefully have a better feel for how you analyze a structure, how you look at a structure, and how you pass loads from one way to another without having to do an advanced 3D model. I'm not against 3D model, I'm just very cautious around them. As let's say now we model this. Let's go back to our 3D model. Imagine you model this in 3D. If you don't model these purlins correctly, it might assume that the purlins act with the roof bracing. Instead of the roof bracing obtaining load, it goes down purlins, and you might add stiffness to the structure that doesn't necessarily exist. A couple of final notes just about a few things if we're looking at the structure. Be very careful with trusses. Section through this thing. If I'm making you dizzy, my apologies, it keeps disappearing. Let's get a truss on its own. When you're designing this, have a look at effective lengths. If I am designing this truss, what is the effective length? How will it buckle? Well, easy. The angle will buckle from there to there, so according to the code, that should be 1 times the length. So people who design to the old code sometimes use 0.85 times the length. But anyway, there's various debates going on around that. So this is verticals, horizontals. But this bottom chord, how do you have a look at it? How do you design for this bottom chord? Well, it will obviously buckle from there to there in plane, as in, if it buckles sideways, it will buckle from here to there. So that is the effective length. When you look at the model, you might think that your effective length is from node to node. So a little bit from node to node, whereas actually it's not. It's from knee brace to knee brace when buckling horizontally. When it buckles vertically, yes, that is the effective length. But buckling horizontally, it's from there to there. So have a look at all these factors, and the same thing with the column. You might think the effective length of this column is from there to there, or from there to there. But just see what prevents it buckling sideways. And that's where either you've got the girths or your knee braces. So it depends also if it's the inner flange or the outer flange. So all these things you have to consider when doing a design and carefully take your loads through. So to come back to the beginning of the structure, the beginning of this lesson, you need to say to yourself, if I apply a load anywhere to the structure, I know where it will go and how it will go through the structure and how it will get out. And if I do an analysis model, I can do a quick calc to just verify what I've done. Alright, I hope you've enjoyed it. I hope you've learned a lot on how to analyze structures. I'm looking forward to seeing what you people can all do in the future. Thanks. Cheers.